sorry, I'm going to repeat that for whoever joins us later. Last time we were playing around with example 341 and 345. And I told you guys that I'd give you a clean copy of everything here in one go. So 341 says we have P types of objects, infinite supply, and we wish to choose K of them. So order matters, and at least one of each. So if we look at this as an occupancy problem, then this is the dessert buffet problem, except I care whether I eat apple pie before pumpkin pie or whatever. And I have to try one of everything. And the parent is there saying, you got to try one of everything. It's going to be rough, but you have to do it. So that means that we're talking about choosing K balls, we have P cells, we have no empties. And so if you look back in chapter 2 and we compared it, we'd see the number of ways to do this was, now I've got my silly letters here, I think the K has switched, right? So it's normally K factorial S of NK, so it'll be P factorial S of K comma P. So that's what we know it to be. We also know it is some function just of K and P. And so let's try to figure out another representation of this function using exponential generating functions. So the exponential generating function for this scenario, we have P types of objects. We have to choose at least one, so we can't choose 0. So we start with x to the 1 plus x squared over 2 plus x cubed over 3 factorial, and so on to the P. Hold on, I flipped a page. Now I don't remember where I was. Here we go. Nope. Oh, there it is. So we have that this is e to the x minus 1 down there to the p, which we can expand using the binomial formula. So this is the sum as I goes from 0 to p of p choose I minus 1 to the I, and then e to the k minus I times x. So then I'm going to use the power series expansion for e to the a. So this is the sum as I goes from 0 to p choose I minus 1 to the I, and then that'll be the sum as doesn't really matter. I'm going to use j. J equals 0 to infinity of, that'll be k minus I to the j, x to the j over j factorial. We can bring our infinite sum to the outside. That's the sum as j goes from 0 to infinity. Then of the sum as I goes from 0 to p. P choose I minus 1 to the I. And then k minus I to the j, x to the j over j factorial. So then that piece in the parentheses there, that is the sequence t of k comma p. So t of k comma p equals the sum as I goes from 0 to p of p choose I minus 1 to the I, k minus I to the j. Now this is not written with the same letters we used, but this means that the Stirling number formula, S of k p equals 1 over p factorial times the sum as I goes from 0 to p choose I minus 1 to the I, k minus I to the j, which we had before. We had S of n comma k equals 1 over k factorial, the sum as I goes from 0 to k k choose I minus 1 to the I, and then damn it, I did it again. I'm sorry, my notes have different letters in them, and I was reading those letters. This should be a p minus I right here. So that should be a p minus I all throughout. And then I should have used a k here, not a j. You know what? Forget it. I'm going to restart that. You just h of x equals x plus x squared over 2. I'm going to stop looking at my notes and just do it for real. So this is e to the x minus 1 to the p. This is the sum as I goes from 0 to p choose I minus 1 to the I, e to the, now that's p minus I times x. Then that's the sum as I goes from 0 to p of p choose I minus 1 to the I, e to the p minus I then becomes the sum as j goes from 0 to infinity of p minus I to the j, x to the j over j factorial. So then this is the sum as j goes from 0 to infinity of p minus I minus 1 to to the I. Oops, nope. I was exchanging my sums. I got to actually write that sum though. The sum as I goes from 0 to infinity to P. P choose I minus 1 to the I. P minus I to the J, X to the J over J factorial. This then is the sequence. Now, we didn't want this sum to be a sum in terms of J. We want this sum to be a sum in terms of K. So all I'm going to do is replace J with K. There's the first replacement, and then X to the K over K factorial. Now this guy here is T of K comma P is the sum as I goes from 0 to P. P choose I minus 1 to the I. P minus I to the K. Didn't I just say I wanted to use K instead of J? Did I leave a J anywhere? Or did you catch me before I caught it? Okay, yeah, I should have, honestly, I should have just run this sum as a sum over K here, and then I wouldn't have had to do that extra step. So this is what we were looking for right up here. And so S of K comma P equals 1 over P factorial T of K comma P. And so that's 1 over P factorial times the sum as I goes from 0 to P. P choose I minus 1 to the I, P minus I to the K. And just with a change of letters, that is the Stirling number formula that we had back in chapter 2. I am apparently completely unable to do that without a false start or a misstep at some point. There are admittedly a lot of letters and, you know, two sums. I'm not trying to make an excuse for myself. I'm just saying that it would be easy to, well, obviously. Anyway, so that's all I was trying to do with that, was to verify that formula we had back in chapter 2. Let's see, what else did we have here before we finish the section? Now I've reshuffled my notes and I lost, there it is. Example 343. So we've got an unlimited supply of red, yellow, and green balls. Use 2 methods to count how many ways there are to choose in order. This is a problem where there's no good reason to use exponential generating functions, except for the fact that we were asked to use 2 methods. So after we say for A, 2 to the 5th equals 32, right? Because I have 2 choices and 5 places and order matters. After I do that, I've got to come up with another way. So we could look for the coefficient of x to the 5th over 5 factorial in the exponential generating function h of x equals, here empties are okay, so that's 1 plus x squared over 2 plus x cubed over 3 factorial, and so on, squared. Now that one's actually not too bad because this is e to the 2x. So we can actually just look and see that this is 1 plus 2x plus 2x squared over 2 plus 2x cubed over 3 factorial, got to keep my parentheses, plus 2x to the 4th over 4 factorial, plus 2x to the 5th over 5 factorial, and so on. So we see that that coefficient is 2 to the 5th. What about B? Oh, sorry, that was just A part 2. What about B? 7 yellow, red, and green balls will just be 3 to the 7th, right? But the other way to do it would be the coefficient of x to the 7 over 7 factorial in, we can just say, how about we just do that? Say e to the 3x. That's my h of x, right? It's going to be this thing, but cubed, because I've got 3 pools of balls. And for the same reason that it was up here, that's going to be 3 to the 7th. Then what about 344? Find the number of code words of length k from an alphabet. So we've got A, B, C, D, E. B occurs an odd number of times. So this will be the coefficient of, we're finding code words of length k, right? So the coefficient of x to the k over k factorial, because code words means that order matters in, and so our generating function here, our exponential generating function is, so for everything but b, we get 1 plus x squared over 2 plus x cubed over 3 factorial, just like usual. So we get that to the 4th. And then we get, for b, we get x plus x cubed over 3 factorial plus x to the 5th over 5 factorial, and so on. So this is equal to e to the x to the 4. And this guy here is equal to e to the x minus e to the minus x over 2. That's actually short for hyperbolic sine, but I know that hyperbolic functions kind of get de-emphasized in our Calc 2. That's true, isn't it? I feel like I've been told that. So you can rationalize that one out for yourself, that if I take the e to the minus x terms, then that puts a negative on all of the odd terms. And then if I subtract that, that cancels all the even terms, but then we've got 2 times each of the odd terms. So we divide by 2. So then we can do a little arithmetic. So that's 1/2 e to the 5x minus e to the 3x. And so now we can write this out as 1/2 times the sum as k goes from 0 to infinity of 5 to the k, x to the k over k factorial, minus the sum as k goes from 0 to infinity of 3 to the k, x to the k over k factorial. And so if I write that together as one generating function, I get something like 5 to the k minus 3 to the k over 2 times x to the k over k factorial summed, which means that the coefficient of x to the k over k factorial is 5 to the k minus 3 to the k over 2. So that is the end of chapter, I forget the number in our book. Is it 5 or 6? It's the end of the generating function chapter. And so a good place to just put a pin in today's lecture and give me a little chance later today to go ahead and get your group projects typed up. I'm going to let you guys know right now that I am going to pull back into some of the exam 1 material just because it's a project and some of that stuff was pretty foundational. So don't be surprised if you see a few questions that might have pertained to it. Cool, I didn't know you guys could set up discussions. Neat. All right. Any questions before we skadoosh? Oh, wow, you get your own little mini Canvas page, basically. Cool. All right. Well, you guys have a good day and shoot me an email with any questions. And I hope to have everything, your assignment for your group project posted by tomorrow. If something goes awry, it might be Friday. But is the extra credit still a thing? I forget what the extra credit was. Did I offer extra credit for anything? Or is it just something you saw in the grade book? Plus I mentioned it. Sometimes I do an extra credit homework assignment. I usually do that a little earlier in the semester and somehow it escaped me this time around. Maybe I'll just post an extra credit question on the group project or something like that to make up for it. That would have the side benefit of usually people don't need the extra credit as much in their homework grade. They usually need it more in their exam grade. And the group project's going to count as an exam grade. So